We've been talking a lot about infinite series, and now we're going to talk about using infinite series to actually define functions. And the most common infinite series used to define and approximate functions is a power series. Power series. So I could have a function f of x defined as the infinite series, so we'll go from n equals 0 to infinity, of a sub n times x minus c to the nth power, where a sub n is just the nth coefficient, and c is some constant, and x, of course, is our variable. So this right over here is a function of x, and it might be a little bit clearer if I expand this out. This is going to be our 0th coefficient times x minus c to the 0th power, which is, of course, this part is just, of course, equal 1, so this would simplify to a sub 0, plus a sub 1 times x minus c to the first power, plus a sub 2 times x minus c to the second power. And we could go on and on and on. And this shows up throughout mathematics. People will often use a finite number of terms of a power series to approximate complex functions. And this allows them to do things in their head. It allows them to get a sense of things. It allows them to operate sometimes easier to operate on functions. And this shows up in electrical engineering, and it shows up even in finance and bond trading. Bond traders will actually use a power series approximation to figure out what a bond price might do, or what the corresponding implied interest rate on a bond might be. But we're not going to worry about that right now. We're just going to deal with it a little bit more mathematically. Now, the one thing that you might see when you look at this, isn't a geometric series where if I make the common ratio x, isn't that a special case of a power series? And you would be correct in assuming that. So let's write down a geometric series where the common ratio is x. So geometric series. So let's define a function g of x as a geometric series where the common ratio is x, instead of the r that were more typically used to represent the common ratio. So n equals 0 to infinity of a times x to the n. So what's the difference between these two things? Well, this is just a special case. We're making c equals 0, and we're making all of these a sub 0, a sub 1, a sub 2, they're all just going to be equal to a. And we know that we can expand this out as a times x to the 0 plus a times x to the first power plus a times x squared, and we just go on and on and on forever. This is an infinite series. Well, we've already seen how we can take this sum. In fact, we've already done multiple examples where we take sums of infinite series, and we've derived the formula that gets us that this is going to be equal to a over 1 minus our common ratio. And in this case, our common ratio is equal to x. What's interesting about this is instead of going from the sum to instead of going from this geometric series expanded form to what the sum needs to be, we can use this to go the other way. If we can get some functions into this form, we can then expand them out as geometric series, or essentially we will find their power series representation, because a geometric series is a special case of a power series. And to show an example of that, let's take the function h of x. H of x is equal to 1 over 3 plus x squared. So I encourage you now to pause this video and try to rewrite this function in this form right over here. And if you can write it in this form, to then go and write it as a geometric series. So I'm assuming you've given a go at it, so let's try to do it. So we want a 1 right over here, and we want to subtract something. So if we want a 1 right over here, let's divide the denominator by 3. So this is equal to, or let's factor out a 3, I should say, 1 over 3 times 1 plus x squared over 3. All I did here is I factored out a 3. I divided 3 by 3, factored it out, and then I factored out a 3 from x squared. So if I were to redistribute, you would get this again. Now I could rewrite this. As, instead of 1 over 3, I could write this as, let me write it this way. I could write it as, so this part right over here, I could write it as 1/3 over 1 and I want to subtract this thing instead. So 1 minus, and I could write negative x squared over 3. Notice, adding x squared over 3 is the same thing as subtracting negative x squared over 3. So now I've written in this form. I have my a. My a would be 1/3. And then my common ratio x is going to be negative x squared over 3. So now I can rewrite h of x. I can say that h of x is going to be equal to the infinite series. So go from n equals 0 to infinity. My a is 1/3. And then my common ratio is negative x squared over 3. I'm going to raise that to the nth power. And so if I wanted to expand it out, and actually maybe I'll write that in the purple. If I wanted to expand this out, what would it look like? Well, this would be equal to, well, the first term, when n is equal to 0, this whole thing just becomes 1. So this is just going to be 1/3. And then the next term, I'm just going to multiply by the common ratio. I'm going to multiply by negative x squared over 3. So this is going to be equal to, negative, so if I take 1/3 and multiply by negative x squared over 3, that's going to be negative x squared over 9. And then if I were to multiply by negative x squared over 3 again, well, now I'm going to get positive x to the 4th over 27. Notice the common ratio. Every time to go from here to there, I have to multiply by negative x squared over 3. To go from there to there, I have to multiply by negative x squared over 3. And I could keep going on and on and on. And if I really wanted to write it in that form, I could just, let me make this a little bit clear. So I could just write this as 1/3 minus 1/9 times x squared plus 1/27 times x to the 4th. And you might say, well, this is almost the same form, but all these forms up here, we had, right here you just have the x to the 0 term and then the x squared term. What about this? Well, remember, you could just make this coefficient 0. So I could even rewrite it like this. I could say this is equal to 1/3 times x to the 0 plus 0 times x to the 1st power plus, or let me write this, minus 1/9 x squared, and then plus 0 times x to the 3rd power, and then plus 1/27 times x to the 4th power. And then notice, I have this in the exact same form. As our original power series. So without using any calculus, we were able to take a function like this, represent it like this, and then find a power series representation for it. And this one, I don't want to confuse you here, but you could ignore these terms because these are just 0, and one of these two is kind of a clean way of viewing it.